Right. Okay, figure 3 shows a uniform beam PQ of weight 240 Newton leaning on a smooth wall and resting on a rough floor, okay, with a minimum inclination angle theta minimum. The coefficient of friction between the beam and the floor is 0.25. Okay? State two conditions for equilibrium of the beam. Okay, so first of all, this is a beam, a rigid body. Okay, we are looking at it as a rigid body, not a particle. Not a particle. Okay, not a particle. So it's a rigid body. So equilibrium of a rigid body, you will have two conditions. So what are the two conditions for equilibrium of rigid body? So I did tell you about this Newton's first law. Okay, last time in previous chapter we learned about particle mass or point mass, equilibrium of point mass. Only have one condition, which is total force equal to 0. Okay, there's no rotational motion here, only linear motion involved. But in rigid body, we involve two kind of motion. We have linear motion and also rotational motion. So it will have two conditions. One is total F equal to 0, yeah, for linear motion, and then for rotational motion, total torque equal to 0. So two conditions, yeah, for rigid body. Not moving around linearly and also not rotating in rotational motion. Okay, I'm not to say it's not rotating, it's just that no resultant torque. Okay, no resultant torque. It still can rotate with constant velocity, just no angular acceleration. Okay, so these are the two conditions. Yeah, so let's write down. So let's write down. Yeah, okay. So question 1. So now we are talking about equilibrium of rigid body. Equilibrium of rigid body. So okay, and I make it bigger already. Yeah. All right. So for rigid body, the two conditions are, the first one. Okay, the first condition is the total force must be 0. Okay. The second condition is the total torque must be 0. So the first one refer to the linear motion. The second one refer to the rotational motion. Okay. Total force equal to 0, total torque equal to 0. Yeah, rigid body. So now number 2, sketch all the forces acting on the beam. So now we are on the beam. Now we thinking of it as a rigid body already. Yeah, it's a rigid body. So when we want to sketch a force, this refer to FBD lah. We need to draw the FBD. Okay, FBD. So for this FBD, we are looking at it as a body, a rigid body, not just a point mass. For a rigid body, you really have to draw the whole rod. You really have to draw the whole rod. Don't draw just a point mass. Okay. For this chapter, yeah. For rigid body, we need to draw the whole rod. Okay. Let's draw it. Yeah. Let's draw it. So question 2, how to draw? Okay. For the rigid body, let us draw it out. Yeah. Okay. Now let us first look at when we want to draw the force for the beam. Let us look at what kind of force exists on the rigid body. So first of all, he says that it has the weight. Okay, it has this beam has a weight. It has a weight. Yeah. So it has W lah. Okay, W. And then smooth wall. That means this one, the wall has no friction. Yeah. The friction is 0. Okay, for the wall, it just has normal force, no friction. And then but the floor is rough. The floor is rough. Okay, rough floor is rough. That means it has the, can say it's static friction. Yeah, that means it has static friction on the floor because you know, this rod is not moving, so we just put static friction. minimum angle inclination. Yeah. So coefficient of friction between the beam and the floor is 0.25. So yeah, this is the mu s lah. Okay, coefficient. I give you the coefficient. This is the mu. This is the mu s. Okay, for the floor. We can write the coefficient of friction mu s here is 0.25. Okay. So what I can say is roughly what I can draw is yeah. This rod, it has the weight. Yeah, weight is from the center. Yeah, here there is a weight. Okay, and then for this one, it has the normal force. Okay, it has the normal force at P. Okay, the wall. This is the wall, and this is the ground. Yeah. So wall has no friction. Yeah, wall is smooth, has no friction. And then for the for the ground, it has friction. So it has both normal force and friction. Okay, so we draw it right. This is normal at Q. Okay, and then friction. Okay, this friction should go to the left or go to the right? What do you think? The friction should go to the left or go to the right for the floor? Do you think the friction should go to the left? Yeah, this friction should go to the left. Is it? Imagine if this rod friction go to the left, that means at this end, at NQ, the floor is pushing the rod to the left. Yeah, pushing the rod to the left. So the rod more tend to fall down. So it's not logic that friction going to the left. Understand? Friction should go to the right. Go to the right. Understand or not? Because why? Because this floor is like tend to slide down. It tend to slide down. Let me draw for you. Yeah, let me draw. Let me draw for you. Okay. Let me tell you this. Yeah. Let me tell you this. Okay. I want to illustrate here. Let's say now we have a rough wall. Okay, let's say this wall is rough and this ground is rough also. Okay, both are rough wall and rough ground. So both wall and ground has friction. Let's say lah. Okay, so the wall has friction, the ground also has friction. But what is the direction of friction? And what is the direction of friction? Okay, let us imagine how this rod will tend to fall down. In which direction it will fall down? Of course, we can imagine something like this. Yeah, we can imagine something like this. This rod is like falling down. Yeah, this rod. If this wall has no friction and this ground also has no friction, this part, yeah, the lower part, it will go to this direction, and the upper part will go to this direction, isn't it? It tend to fall down. You know, the rod tend to slide down. The rod tend to slide down. So in the next second, maybe it becomes like that already. Yeah, maybe it becomes in next second, when it fall down, it goes to this direction. Isn't it? You understand or not? In the end, after it fall down, it become like that lah. On the floor already. Oops, sorry. See that? So the rod tend to slide down. That means what I can say, the end at part P, it tend to slide down, go downward. And then after that, go downward some more. And then fall to the ground. And then for the NQ, it tend to go to the left. You see that? It tends to go to the left. In the end, it goes to here. Right? So what do you think is the direction of friction for the wall and also for the ground? So we can see clearly already. So for the wall, because this rod, it doesn't go up. It actually coming down. It tends to slide down. So the friction should actually hold up. The friction for P tend to hold up. We can write this static friction at point P. And then for NQ, the static friction should go to the right. Yes, static friction should go to the right. For this is for Q. You understand? So if the wall is rough, then this is the normal force and this is the direction of friction, because the rod will just go down, it won't go up unless somebody pushing this rod to the right. Then this part will go up. You understand or not? So the motion is tend to go down, so friction is actually supporting upward. Okay, so and then for NQ, this rod actually is tend to slide down, so this end will not go to the right. This end will not go to the right. Actually, it tend to go to the left. Understand or not? Tend to go to the left. So friction, the friction from the ground is supporting it to the right. Yeah. So what we can say is friction always oppose the motion. You see, motion is going down. Friction is opposed the motion going up. The motion for N below here is the motion is to the left. Motion is to the left. The rod tend to the left, but friction is opposing the motion, supporting the rod. So friction go to the right, oppose the motion. Okay. So we can say write something here. So friction always opposes the motion. Opposes the motion. Okay, so now looking from here, we can actually find out the resultant reaction force. You can say that these two can be combined. Yeah, these two forces can be combined. Okay, can be combined. Yeah, we can combine these and we make one new forces. This is a reaction force at P. You understand? That means this normal force become the X component, and this friction become the Y component. The X component and Y component combined become a reaction force at point P. Whereas for this part, normal force and friction, this one also become another reaction force. Maybe we should use what color should I use? Use a black color. Yeah. Okay. So this one, these two forces combined, we get another force. This is a reaction force at point Q. You understand not? That means this friction here become the X component, and this normal force become the Y component for reaction Q. In other words, we can redraw the diagram become this one. Okay, in other words, we can redraw this diagram become like this. Okay, first of all, the weight. Yeah, we draw the weight at the center. Okay, the weight at the center. Yeah, the rod has weight. And then at P, this normal force we can just write as reaction X. We can write as what? RXP. That means the X component. This normal force actually is the reaction force, the X component of reaction force at P. Yeah, and this friction become the RY. This friction become the RY. You understand or not? And then this combined is what? It is the RP, the reaction force at P, if the wall is rough. Okay, if the wall is rough, that's it. Yeah. And then how about the NQ here? So this friction on Q is the RX, is the X component. RX for Q, whereas the normal force is the RY. Is the RY. RY for Q. You understand? So these two combined, we will get what? We will get RQ. We will get RQ. You see that? Just that simple. So if this is a rough wall, rough ground, this is what? This is lah. We have RXP, RYQ, yeah, RYP. This is actually the normal force, and this is actually the friction combine, we get the reaction force at P. Okay, and for this Q, we have RXQ, we have RYQ. This RXQ is actually the friction, and this RYQ is actually the normal force. So combined, we get the RQ, reaction force at Q. Okay, so now back to our questions. So just now he say this is a smooth wall. Okay, so this is just a smooth wall. Okay, this is a smooth wall, whereas this is the rough ground. Okay, so smooth wall has no friction, just normal force. Okay, so we can just write it as this is the normal force at P. Okay, and just we have drawn already just now actually also, and then the weight, and then what else? We have this friction. So we can actually just write as RXQ and RYQ. Yeah, we can write as RXQ. This is RXQ, and this is RYQ. And then combine, we have the RQ. Understand not? RQ. Okay. Yeah, this is RQ. So yeah, the X component and Y component. Understand? So these are the forces on the beam. Okay. But one thing I want to tell you is, you can see here this reaction force. Maybe let me redraw for you. One thing I want to tell you that you can see here actually there's two angles. You can see here this theta minimum is just now the angle for the rod. Yeah, the angle for the rod. Yeah, theta minimum. Theta minimum is the angle for the rod. Whereas here got another angle theta. This one is the angle for the reaction force Q. Reaction force Q. I want to ask you, is this theta and this theta minimum has any relationship? Do they has any relationship? No, they are not related. So this theta, this angle theta for the reaction is not the same. It's not the same as the angle for the beam. Okay, it's not the same. So we cannot say, oh, the reaction force angle is the same angle as the angle theta for the beam. No, yeah. So this theta, you have to find out after you know the Rx and Ry. You can only know the angle theta after you know Rx and Ry. That means you still have to use Ry divided by Rx, use tangent theta to find the angle for, to find the angle for what? To find the angle for the reaction Q. The angle for reaction Q is not the same. Yeah, remember, it's not the same as the angle for the beam. Okay, you want to find the angle theta, you cannot use the angle theta minimum. You want to find angle theta, you need to use tangent theta, Ry divided by Rx. Once you know Ry and Rx, only you can find theta. Yeah, this theta is not the same as the theta minimum for the beam. Okay? Okay, that's one thing to note. Yeah. So this is the free body diagram for rigid body. Especially for rigid body. Not a particle. Okay, for not a particle. Remember, this is not a particle. That's why the free body diagram for a rigid body, we draw the forces at different point of the body. Yeah, some forces over here, some forces below. You see that at different point. For particle, all the forces act at the same point, act at one point. But for rigid body, all the forces act at different point. Because now we don't think about linear motion only. We think about rotational motion also. Yeah, forces at different point can lead to the object being rotated clockwise or anti-clockwise. That's what we call rigid body, has rotational motion. Understand? So for rigid body, you need to draw the whole body. You need to draw the whole body, not just a particle. You need to draw the whole body. And then you need to draw the forces at different point. Draw forces at different point. This one you can either put Rx, Ry, or you can also put as friction, normal force. You can write like this also can, or you want to write like this also can. Yeah, so has two choices. They are the same. This friction is the same as Rx. This normal force is same as Ry for Q. Okay, so in the end we have Rq, which is combination of friction and normal force. Okay, so that's all for part 1 and part 2. Okay, the question 1 and question 2. In the next video, I will continue with question 3 to 5. Okay, thank you.